Today we're going to be looking at a problem involving a 2,000-pound wrecking ball. In this case, we're looking at is a work energy practice problem. This is the third work problem available. In this case, we have a 2,000-pound wrecking ball that hangs from a 40-foot cable, and what we're going to be treating this or taking into account is the idea that the cable is going to be considered to be inextensible, so that the 40-foot length will remain unchanged while it swings through this 40-degree curve. So what we're looking for is we want to have an estimation of what is the expected maximum velocity when the ball reaches the bottom region. Now, as you can see, we're looking at the sketch and we're expressing the fact that we have a 40-foot cable both at the beginning and the end. We're sweeping it through this circular arc accordingly, and you're having this 40-degree angle due to the starting point. As a result, when we're looking at something like this, we can now go in and observe the fact that we have an expected change in height, so we have a delta H. That delta H, as a result, is observable in that we have this 90-degree angle that we can observe here, allowing us to find that due to geometry or trigonometry, we can observe that the change in height, the initial height and the final height, is an aspect that this delta H is a resulting difference between the vertical portion of the left-hand side of this right triangle, where we have the hypotenuse length of the cable, where we have 40 multiplied by the cosine of that 40-degree angle. And we're able to subtract off the known height or known length of the cable when it would be in its vertical position. So what we're looking at is we're subtracting off the vertical portion of that triangle to know how much really are we dropping in height. When we complete that calculation, 40 multiplied by the cosine of 40 degrees, we find that we obtain a change in height of negative 9.36 feet. Now, what that allows us to observe is the fact that we have a height change in which we are dropping down in height, which, if we return to our definitions of potential energy, going from a high height to a low height is a negative decrease in potential energy, which, if everything is accounted for, should result in a gain in kinetic energy or another form of potential energy. In this case, we strictly are looking at a height change causing movement, so we have kinetic energy being, so to speak, created while we're losing potential energy. So that transition of energy from one state or one status to another, from potential energy to kinetic energy, is what we're looking at here. And we can observe the idea that no external work is completed. So external work, W, being equal to any change in kinetic energy plus any change in potential energy, is kind of where we can go with this. If you recall from conservation of energy equation, we can say that the kinetic energy initial plus the potential energy initial plus any work to go from an initial state to a secondary state is equal to the kinetic energy at that ending state and the potential energy at that ending state. In this case, as a result of no external work being completed, we can observe that that work is equal to 0. The change in potential energy is 1/2 multiplied by the mass that we have present multiplied by the change that we have present in kinetic energy. Well, in this case, we have V final squared. V initial, because it's being released from rest, or assumed to be from rest, we have 0 initial velocity. And our change in potential energy is where we're able to now come in and say that we have an mg multiplied by a delta H. As a result, we can now plug these in. Now remember, because we're dealing with 2,000 pounds for the weight, we need to account for mass being equal to the weight divided by our G, our conversion aspect, due to gravity. The acceleration due to gravity in US customary is 32.2 feet per second squared, so we divide by the 32.2, and we have our final velocity squared. Plus, mass times gravity is our weight, so we can bring in just the 2,000 pounds and multiply that by our delta H, which is the negative 9.36. As a result of solving this through, we can find that our final velocity is equal to approximately 24.55 feet per second. And that provides us a methodology for finding final velocity as a result of a change in height or a change in potential energy.